Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you.
So in our previous video, we generated a time series model for our image and our locations within our region of interest. And I thought it was quite interesting in the sense that we also tested it in Excel, and we found that we could, it works perfectly in Excel, and we also understood the time element of it, the time identification of it, etc. So it was always nice to just put it in an Excel format, because for me personally, when I do it in Excel, it makes a lot of sense. I can understand what I'm doing in Excel. So by replicating what we've done in Earth Engine in Excel, it made a lot of sense to me. Now I understand it so much better than if I didn't do it in Excel. But to show you, that what you can do in Google Earth, you can also do in Excel, but you need the data. You need the underlying observations to be able to work in Excel. And that's the beauty of Earth Engine, is generating that specific data. Okay, so we're going to continue where we left off. Remember, we're still working on something similar to what we've done in RStudio. Remember, in RStudio, we take a time series like what we've done here. This is also maximum temperature, same what we've done in Earth Engine, and then we detrend this or decompose it. Okay, so we first detrend it in a trend. Now in R, we generated a linear trend. So this is a non-linear trend, but we generate a linear trend. And obviously, if we subtract the actual observations from the linear trend, we should then be left with seasons and random. If we assume that there's no random, then if we take the actual observations, the actual time series, we subtract the trend, we should be left with what we call the seasonal patterns. Okay, so obviously in our case with maximum temperatures, if you look at this particular time series, then it's obviously there's a seasonal element to it, which makes sense because it's climate, so that makes sense. And so what we've done is we've determined a trend in it. So what we want to do now is to take the actual seasonal the actual observations and subtract the trend, so that what we left is the seasonal values. Okay, so remember the trend, the red line here, plus the seasonal values will give you the actual values or the observations. Okay, so to a large degree we've already done the trend, we've got it, so it's simply just a matter of subtracting it from one another. And we showed in Excel, for example, that it's indeed possible to model what we've done in Earth Engine by using the coefficients. Okay, so remember the coefficients is what we generate up here with these functions, is where we generate the coefficients. As I said, you just basically down, you can see there's the coefficients of the trend itself, that 5.776 the power of minus 5e and a 22.618. So that's what we've done in the previous. All makes sense, all happy. Now, as I said, what we want to do in Google Earth is basically generate the seasonal pattern, similar to what we've done in RStudio. Now in RStudio, it's just fairly straightforward. It's 3 pieces of code, and there we go. Just that 3 pieces of code to generate this whole thing. And obviously you can save the data as is. Okay, so in RStudio it's very straightforward, nothing too much to do it, because you have packages that works with it, and there's your time series package. Okay, nonetheless, let's proceed in Earth Engine. So what we do first, it's pretty much still continuing with the main thrust of the previous pieces of script of code, in that we have our variable, in this case maximum temperatures, which is our dependent variable, and then we create 2 independent variables. We create a constant and we create a time variable. Okay, now we've already indicated in our previous video how we create the time variable and what it looks like. And remember, so it's not January 1960, it actually converts a January 1960 in a value, in in a number. Okay, and that's why we use a float. Anyway, so continuing. So what we're going to do is we're going to create, work with linear modeling of time. So similar to what we've done with above here, where we calculate a linear trend, it's exactly the same thing, just a little bit different in the sense that it gives you slightly different outcomes, but nothing serious. Okay, so let's have a look where we are. Again, we create our independence, okay, constant and t. Similar to what we've done here. You see here in the previous code, we also create a constant and a linear trend. You see, there's my linear trend t, which is a float, and there's my constant. And the linear trend comes from our system ID, our time ID, which is a number. Okay, so that should be sorted now. So we work with our independence, and then we create our dependence. So there we create our regression again. This is this formula. So that's your dependent. This is your constant, which is independent, and this is your time variable, which is also independent, and its coefficients. Okay, so that's basically what we've created there. Now we're generating this actual equation. And this is what this basically means, is we are generating our equation, but not for the actual values itself, not for y, but for the trend, meaning for that value there, the trend value there. Okay, this value here, that one there, that's our trend. And so we're calculating our trend variable. Okay, so that's what we're doing. So we've got our independence, which is, remember what's our independent, is our constant, and we add that to our dependent. What's our dependent? It's maximum temperature. We generate a regression, and it's a normal, there's no lag variables, etc., etc. So play around with these numbers to see what the outcomes are, but it's basically there's no lags to any of the independent variables. Okay, and then we simply add that layer to our layers. There it sits. Okay, trend array image. There it sits. Okay, so we can work on that. Remember, there's our climate trend that we've generated previously. It's just going to load now. So while we're talking now, let's keep them activated. Then we flatten the coefficients, and that's just to make it easier to work with. So those are the coefficients that we generate. So that is this value here, the beta 0 value and the beta 1 value. That's what we call our coefficients. That's what we're generating there, is these coefficients. Okay, so we take this trend, this regression here, okay, and then we calculate its coefficients. So remember, this is the regression equation. We generate its location, similar to what we do in normal OLS, nothing different, and we call that coefficients. Okay, then we take our coefficients, okay, and we reduce it by the sum, and we generate our detrended seasonal graph. This one here, you see, that's the detrended, so that's a detrended. See, that's the graph here. So our detrended, it's filtered image, and we take our image, our dependent, remember that is our dependent here, TMX, and then we subtract our independent variables, multiply by its coefficients. Okay, so we're taking basically our y, and then we generate our trend using our independent variables, and then we subtract the two. Call it an error term. So that's basically what we calculated, but we're just saying it's not, we didn't say it's an error term, we're actually saying it's a seasonal component. But that's basically what we're doing there. So we're basically taking this, remember we've calculated the trend there, so it's going to be TMMX minus y is equal to this whole thing for each specific date. Okay, and we're using a sum reducer. Okay, we're using a sum reducer because we want to generate the absolute numbers, and that's why we generate some. But again, play around with the value there and see what comes out, what the results look, and then you determine whether it's reasonable or logical. So that's basically what we're doing. We're creating a trend regression, this one here. Okay, and then from the trend regression, we're generating the coefficients, which we show you those coefficients there. And then what we're doing here, okay, this is what we're doing here. We're taking our dependent variable, TMX, unmodeled as is, the actual observations, and we subtract the trend. Okay, this one here, we subtract that thing there. And that's what we get to our detrended, or our if in this case, our seasonal pattern. Okay, so remember what I said here. If I open this up, this value here, the seasonal, is my observed minus my trend. Okay. Yeah, as I said, the idea of this decomposition is to take the observations, generate the trend. If we subtract these two, if we assume random is 0, what should be left is the seasonal patterns. Okay, so that's exactly what we're doing in our code here. Okay, as I've been explaining for the last couple of minutes. Okay, so remember there's our timestamp again. Remember, as we said in our previous video tutorial, what Earth Engine does, it generates January 1960. It takes January 1960 and converts it into an absolute number, into a value, which basically equates to January 1960. So that value is unique because it's not February or March. That value is unique because it's January 1960. And I showed it in the previous video how you can do that in Excel. Okay, so this is basically what we're doing here. We're generating a linear trend. Okay, we're generating a linear trend. And then from that linear trend, we subtract our observations. And what is left is our seasonal component. Now, you could also then basically say, if you look at this equation, you can say, is ignore that n variable, that would be our error term. Okay, so this pattern here, this seasonal pattern, you can also equate to the error term in our normal standard OLS equation. Okay, and then we're basically just charting that and this is what it looks like. Okay, so we chart our series, our detrended. What's our detrended? Our detrended is our dependent value, the dependent value subtracted by the trend, and this is what the trend is. It's the independence multiplied by the coefficients, meaning this thing here. Okay, so that's how we get to this particular time series. So this is a seasonal time series or an error term time series. Okay, so we plot it. You can again play around, make it pretty, change the length and the width and all these things. Now, this is a scale factor. Now, this is quite important for you to note. If I make that, for example, 30, then this will never load. It's not going to load, and it will run and run and run. Eventually, it will time out. So, make sure that this variable here is appropriate for your time series or for your calculation. It should be small enough to run this, but not so that you run into time constraints. So play around with this time scale value here. Okay, make it be if you're running into time problems because you've got too large region of interest or too many data points or whatever the case might be. If you get into timeouts, just make that number bigger and bigger and bigger. So I also struggled with this. The data came after, it just ran and ran, I think for about 10 minutes, eventually gave me a timeout warning. It went down and yeah, it's all because of this particular value. So play around with the values. As I said, there's my name, line width, etc. So, and I then did print it. And this is what I get to. Okay, so similar to what we've done previously or in our previous video tutorial, let's expand it. This is our seasonal patterns. You'll see it's got a range of a variance. Let me put it that way. It's got a variance of between 8 and -8, positive 8 and -8. The variance looks fairly constant, and the variance for obvious of the season patterns obviously are mean reverting. So it's got all the elements of a stationary time series. Okay, remember I said previously this is a trend stationary time series because it's got a slight trend. The trend is not mean reverting, it's got a slight upward trend, therefore that coefficient is upwards, although it's very, very small. But the seasonal behavior of our maximum temperatures certainly seems stationary, and a constant variance, mean reverting, all that nice things that you want in a time series. Okay, so we can download that. So I press download, choose a place to save it. You can give it another name. Let's ignore that. It's downloaded now. Let's open it up, and it's going to obviously open in a CSV file. Okay, now in CSV you can't do anything, so I'm just going to open it up. Just select all the data. I go to data, text to columns, delimited it, next, comma, and finish. Now I'm just going to copy this text of this data, because remember, this is now the seasonal values. Okay, this is now the seasonal values. So I copy this, and I go to my original one, and I paste it in. There it sits. Okay, so I paste it in. Okay, now mine doesn't, it's pasted in as points. It sees now as text, so I need to convert it into numbers. I go find, I found the dots, the points, and I place it with commas. I place all, and it's done. So this is the seasonal pattern, so call it seasonal. Seasonal. Okay, so let's have a look and see what the error term is in our regression model. Okay, so remember, this is our error term in our regression model. And how do I calculate this? This is the actual values minus my estimated values. Remember, so that's the actual value. Remember, this is my linear trend, this one here. Okay, in the previous model. Okay, so this is the error term, which is the difference between that and the linear trend, and this is my seasonal. So if I highlight them both, and we're going to overlay the two now, which is the seasonal pattern and the error term. I go to insert, I go to, and you'll see that we cut it quickly, go paste it in the top here. Paste it in there. You'll see the two are basically identical. That's why I say, okay, so the two are basically identical. You can see so let's just quickly make the one more transparent for my data series. Let's make it a little bit more transparent. Okay, it's not gonna, so let's make it yellow, and let's change the transparency. You can see there, well, you get the idea. Let's make it dots. Okay, let's make it dots. There we go, the blue dots, the orange dots, and let's make it a little bit bigger and make that transparent. And then so that's the background color. Let's make it red. Maybe it will stand out a bit more. I won't. Okay, yeah, you can see there. But anyway, so moral of the story is, it's a little bit difficult. I need a bit more time to play around with this, but the moral of the story is that the two series here that we've generated, okay, are virtually identical. Yes, there's subtle differences on the decimal side. You see that there's a 0.2, there's a 0.2, there's a 0.3, there's a 0.2. So on the decimal side, the error term, which is this one here, and the seasonal pattern that we've calculated are basically the same thing. Why? Because in both cases we generated this equation. In the one we call it seasonal, and the other one we call it error term. Okay, so if I take the seasonal pattern that we just calculated and I subtract it from the observations, remember this is the observations, this is the trend. Remember this value here is this thing here that we've calculated. And this is calculated using these two coefficients, if you can remember correctly from our previous tutorial. So if I take, for example, and I take the actual values, this one, and I subtract the seasonal patterns, I also get to a trend. Now, if I generate the trend value of this one and this value, it should be roughly the same. Okay, so let's quickly just get the two of them in one graph. And because the error term and the seasonal pattern are the same, it stands to reason that the two trend terms should be almost the same. And there they go, very similar. Okay, which one is on top? This one is, okay, so this one is the linear trend which we've calculated in the previous video, and this is the trend that we've calculated in the current video. But you can see they both basically have the same. So they have a different slope. You can see the slope is a little bit different. The constant are a little bit different. You can see the constant are different. But the slope, meaning the time coefficient, are exactly the same. It looks very, very similar to one another. So yeah, so generating the error term by subtracting the observed in the trend and calculating the seasonal pattern, this one seems to yielding exactly the same outcomes, the same results, which is not surprising because it's, it's still the variables are exactly the same. It is the dependent variable, which is your maximum temperature, and then it generates a time variable, which is exactly the same because it's all coming from the same image collection, and therefore they will have the same timestamp. So the only difference, as I said, is the constant. That's the only difference in generating these different graphs or time series. Yeah, so that's the seasonal part. Okay, so in Google Earth, we've now basically calculated this particular variable here, assuming that that's 0. And as I said, we can replicate what we've done also in Excel. And the two sets of series should basically be exactly the same. So whether you use the linear modeling of time or the linear trend of the images, the results are very similar because, again, whether you calculate the time there or the time here, and the constant, as I said, is exactly the same. But nonetheless, play around with the variables a bit and see what happens. It should give you results that's quite interesting. Play around with the sum, use median on average and see what the results looks like. Well, let's do it quickly. Median and see what the results look like. Remember, let's keep it open. Let's run it again and see what the seasonal pattern looks like now. And as I said, remember this variable here. That's quite a tricky one. That's an important one because that will decide whether your images actually, your charts actually generates or not. You see now, it's now going to give us a problem. Remember, there's our no. You can see that, it's quite different, in the sense that now it is much higher. You look there, there's the sum variables, which is between 8 and 8, which makes sense. And here it's between 6 and 20. The seasonal patterns cannot be that. If we go into you can see there's the seasonal patterns in RStudio is between -6 and +6. So that should be the seasonal patterns. Seasonal pattern cannot be that. So that's what I'm saying. Play around with the numbers and see what happens. So it cannot be median, and so therefore it cannot be mean as well. So it must be sum. So that's what I'm saying. Always play around with these variables that you can change. I said, just remind again, remember the system start. Remember we had it here as well, system start, system end. That is, I go to Excel, that is the dates converted into a value. Okay, so that's how Google Earth generates a value from the time. That's by using that method. Okay, so that was a quickie. Linear modeling of time, as I said, is similar to what we've done previously, just a different way, but it's getting the same outcomes. And as I said, you've got this variable. So if you calculate this and you know the actual, you can subtract the 2, and that should give you your trend. So if you don't have the trend, what we've done here, you can simply calculate this, work backwards. As I said, the numbers should look very, very similar. So there's 2 different ways of calculating roughly the same thing, and that basically is decomposing our time series into its actual trend and its seasonal patterns. Okay. Yeah. So. And then obviously generating the coefficients. That's quite important because you can use that to estimate unknown future values of maximum temperatures for different locations. But remember, it's based on the assumption that's linearity. Our trend is linear. Okay. Well, that's good news. Yeah, perfect. stay tuned. We've got one more to do, and this is this harmonic model where we're going to model the time series itself. So this is what we want to generate. Okay, is a model of the time series itself. So not a linear model or a seasonal model. We want to model the time series itself, and that's what we call harmonic model. Okay, harmonic regression. Now, just on this, remember all of this stuff you can fairly easily, well, you can do it in Excel to some degree. Okay, and then you can do it in RStudio. My personal preference is not to do this in Earth Engine. You can see all the stuff that you have to do. You do something wrong, the whole thing bombs out. I prefer to work either in Excel or RStudio, but obviously I always generate my images and my data in Earth Engine, and then I export it. As soon as it's exported, I can do so many more things with it. But this is just a video tutorial to explain or to demonstrate how it's possible to do those work also in Earth Engine. And it might be possible to do everything in Earth Engine simply because of consistency. You're not open to manipulation of the data. You work with consistency. Okay, but anyway, that's up to you as the researcher or the analyst to determine how you want to proceed going forward. Okay, well, let's stop blah blah blahing now. I think I've said enough. This was again for me very interesting, and from what's interesting, remember what I said in the beginning. It's what I can do with the data set, not necessarily the outcomes of it, the results of it, but what I can do with this. It demonstrates the power of Earth Engine, that you can do all these things with it. It's a time series, GIS, everything in one, but it's a bit of effort coding. But you can do everything. As I said, I prefer Excel, RStudio, QGIS, and Geoda. And then if you want to do eViews, you can do a bit of eViews. But yeah, that's still in the process. Okay, stay tuned. Thanks for being with me on this ride, on this journey of remote sensing. I really thoroughly enjoying your company. So nice to have eager beavers on board. I really appreciate it. Remember, caring is sharing. Please forward, like, subscribe, all the fancy things. And then I'll see you on the other side.